Welcome to this comprehensive SwiftUI guide. Today we'll explore one of SwiftUI's most powerful features, the Searchable Modifier. Whether you're building a content-rich app or a data-driven interface, mastering this modifier will allow you to create seamless search experiences that your users will love. Follow us as we unlock the potential of SwiftUI's search functionality and learn how to implement it in your applications. We'll start by adding a search bar and filtering capabilities to our task list, demonstrating how to efficiently filter data based on user input. Next, we'll explore essential searchable parameters, including search bar placement options and the searchScopes modifier, a feature that allows users to narrow their search within specific categories or criteria. Finally, we'll learn how to create and customize our own search implementation, giving you complete control over the search bar's appearance and behavior. By the end of this section, you'll be able to implement sophisticated search features in your own applications. So let's get started. Before diving into implementing advanced search and filter functionality in our SwiftUI app, let's examine a foundational example that demonstrates list management in SwiftUI. We'll start with a simple task management interface that will help us understand the core concepts of search and filtering operations. The example consists of a task list view that leverages SwiftUI's navigation stack for seamless navigation and state management through a shared environment object application data instance. Our custom task cell view efficiently presents each task's properties, title, description, and due date, using VStack layout. We've also implemented swipe to delete functionality using SwiftUI's native onDelete modifier, ensuring data consistency between our filtered view and the source data. Let's begin by examining the data model structure, which forms the backbone of our implementation. The foundation of the app revolves around the task struct, which implements identifiable and hashable protocols for seamless SwiftUI integration. Each task contains essential properties like ID, title, description, due date, category, and completion status. At its core, the application utilizes the modern observable macro through the application data class, which eliminates the need for manual state management while maintaining thread safety via unchecked sendable. The data architecture employs a sophisticated two-tier system where observation ignored user data stores the source information, while filtered items handles the processed data for display, automatically updating when changes occur. The application implements an intelligent search system that provides real-time filtering across task properties, featuring case-insensitive search capabilities across both titles and descriptions, automatic alphabetical sorting, and locale-aware string comparison. For consistent data access throughout the app, we employ a singleton pattern through a static shared instance, complemented by a standardized date formatting system. The initial data structure encompasses a diverse range of tasks split between work-related items and personal tasks. By calling filter values, search empty strings during initialization, we establish a consistent initial state for our task list, ensuring that filtered items is properly populated and sorted before the user interface is rendered. The result is a scalable, maintainable task management solution that leverages the full power of modern Swift programming patterns while providing a smooth, responsive user experience. Now let's modify our view's layout to implement a search feature, which will allow users to filter through their tasks. First, we'll declare a state property search term of type string using the state private property wrapper, initialized with an empty string. This creates a mutable state variable that will store the user's search input and automatically trigger view updates when its value changes. Next, we'll add the search functionality to our navigation stack by applying the searchable modifier with the following syntax. The $search term syntax is particularly important here. It's a fundamental concept in SwiftUI known as a binding. When we prefix our state variable with the $symbol, we're creating a two-way connection between our user interface and the underlying data. While searchTerm directly accesses the value of our state variable, searchTerm creates a binding that not only reads the current value, but also allows the search field to update this value as the user types. This two-way binding is essential for interactive features like search bars, where we need to both display the current search text and capture any changes the user makes. The prompt parameter provides placeholder text that appears when the search field is empty, guiding users on its purpose. To implement a functional search feature, we'll utilize the onChange modifier to monitor search input in real time. Start by implementing the core search functionality. This code creates a responsive search experience by watching for changes in the search term property, cleaning the input by removing extra spaces, and automatically updating filtered results. The closure parameters old and value serve specific purposes. Old represents the previous search term before the change, while value contains the new, current search input. This dual parameter system allows you to compare changes and implement more complex search logic if needed, such as detecting when users clear the search field, when value becomes empty, or tracking search pattern changes. When a user types in the search field, the modifier immediately captures these changes and processes them. The initial false parameter prevents unnecessary filtering when the view first loads, optimizing performance. The trimming characters in whitespaces method ensures clean search input by removing any leading or trailing spaces that might affect search accuracy. The appdata.filterValues search function then processes this cleaned search term to filter your data array, updating the UI with matching results. To create a more user-friendly interface, you'll want to maintain search bar visibility during content navigation. Add the following parameter to your search bar implementation. This placement modifier anchors the search bar at the top of the screen, ensuring it remains accessible even as users scroll through extensive content. The Always Display mode guarantees consistent visibility, preventing the search bar from disappearing during crucial search operations and maintaining a seamless user experience throughout your application. With the search feature fully implemented and functional, we'll expand our task management app's filtering capabilities by implementing category-based sorting, specifically distinguishing between work and personal tasks. First, we'll create a custom enum called Scopes. This enum will contain two cases, work and personal, serving as our primary filtering categories. First, it enforces type safety at compile time, preventing runtime errors from invalid category assignments. Second, it creates a clear, finite set of mutually exclusive options that perfectly matches our task categorization needs. Finally, it enhances code readability by making our filtering logic more expressive and maintainable. To integrate this new filtering capability, we'll modify our existing filter values function to accept a scope parameter of type scopes, defaulting to .work. This parameter will work alongside our existing search functionality, creating a more robust filtering system that can handle both text searches and category-based filtering simultaneously. The first stage of filtering implements a category-based filtering mechanism using Swift's enum pattern matching. When the filter values function is called, it first creates a temporary array, filtered by category, to store the initial filtered results. Using a switch statement on the scope parameter, which can only be work or personal thanks to the enum, it filters the main user data array using Swift's filter method. For the work case, it keeps only tasks where the category property exactly matches the string work, while for the personal case, it keeps tasks where the category matches personal. This filtering is done using a closure pass to the filter method, where 0 refers to each task in the array being checked. The result is that filtered by category will contain only the tasks that match the selected scope, effectively creating a subset of tasks based on their category before moving on to any search text filtering. This approach is particularly efficient because it reduces the dataset that needs to be searched in the second stage of filtering. The second stage of filtering represents a significant improvement in the filtering logic implementation. In the first version, the code was performing search filtering directly on the complete user data array, which meant it wasn't taking into account any category-based filtering. This new version shows an enhanced approach where the filtering is performed on filtered by category instead of user data, meaning it's working with data that has already been pre-filtered by category, work, or personal, in the first filtering stage. This change implements a proper two-stage filtering system, where category filtering is applied first, followed by search text filtering, ensuring that searches are always constrained within the selected category. This not only makes the search more accurate and contextually relevant, but also potentially more efficient, as it's searching through a smaller dataset that's already been filtered by category. Additionally, the code has been made more concise by using Swift's shorthand syntax for closure parameters $0 instead of the explicit item and declaration, while maintaining the same functionality. Back to your content view, we'll implement the searchScope functionality using the searchScopes modifier. This modifier creates a segmented control below your search field, allowing users to filter their search results by category. Think of scope buttons as filter tabs. They help narrow down search results based on specific categories. First, we'll add a state property to manage our search. Place this modifier right after your searchable modifier. The search scope binding ensures your view automatically updates whenever the user selects a different scope. Each text view with a tag creates a clickable scope button. When a user taps a scope button, it triggers the onChange modifier, which then updates your search results through the perform search function. This implementation creates an intuitive filtering system where users can easily switch between viewing their work and personal tasks while searching. Let's implement the essential perform search function that powers our app's search capabilities. This function plays a crucial role in filtering data based on user input. The function performs two key operations. First, it cleans the user's input by removing unnecessary white space using Swift's built-in trimming characters method. This ensures consistent search results regardless of accidental spaces. Then, it utilizes our appDataObject's filter values method, passing both the clean search term and the current search scope, which can be either work or personal. This function acts as a bridge between the user's search input and your app's filtering logic. Each time the user types in the search field or changes the scope, this function is called to update the filtered results. A good real-world analogy would be a smart filing system. When you tell it what you're looking for, search term, and where to look, scope, it immediately starts filtering through your files to show only the relevant items. Next, we'll update our onChange modifiers to create a more efficient search implementation. We'll refactor our code by moving the search logic into a dedicated perform search function, which will handle both search term and scope changes. This refactoring brings several improvements to your SwiftUI app. The search logic now lives in a single, reusable perform search function, instead of being embedded in the onChange modifier. By implementing two separate onChange modifiers, your app can respond to changes in both the search text and the selected scope. We're using the simplified closure syntax with underscores since we don't need the old and new values. Both modifiers trigger the same perform search function. This approach makes your code more organized and easier to maintain, as all search-related logic is centralized in one function that handles both search term and scope changes. Now let's implement our newly acquired knowledge on our task management app by adding the search functionality on our custom search field component to help users efficiently filter and find their tasks. To master this custom layout implementation, visit designcode.io and enroll in the Build a SwiftUI App with Claude AI course. This comprehensive course guides you through integrating AI capabilities into your SwiftUI workflow, covering everything from static view construction to advanced interactive features. You'll learn how to design responsive layouts, implement AI-powered functionality, and create engaging user interfaces using SwiftUI's declarative syntax. The course provides step-by-step instructions and practical examples to help you build production-ready applications. Before we begin organizing our home view, let's establish a clear structure to improve code readability and maintenance. First, locate the search bar component and uncomment it, then comment out both task status card and task category tabs components. While it's generally recommended to separate components into individual files, we kept everything in one file for this tutorial. To better manage our code, let's collapse all struct definitions using the keyboard shortcut by pressing Option plus Command plus left arrow. This will give us a better overview of our file structure. For improved organization, we'll move the preview provider to the bottom of the file and implement mark comments to create distinct sections. Here's how we'll structure our code. Add a first header section and group all header-related components. A second one for card section, a third one for task section, and a fourth one for tab bar section. These mark comments serve as visual anchors in Xcode's jump bar and make code navigation more efficient. You can access these sections quickly using Xcode's minimap or the jump bar at the top of the editor. This organization pattern follows SwiftUI best practices and will make our code more maintainable as we continue development. Remember, while this file structure works for our tutorial, in a production environment, you'd typically want to modularize these components into separate files. We're ready to begin. Let's modify our code to implement search and filtering functionalities. First, we'll start by adding a task model that will help structure our data, providing clarity and scalability, especially in applications where each task consists of multiple attributes, such as a title, subtitle, or image. By using a model, we encapsulate these properties into a single type, making it easier to manage and manipulate tasks within our code. For instance, the task model allows us to store and retrieve task-specific information in a structured format, which is essential for features like filtering and displaying tasks. If your tasks are simple and static, such as a plain list of strings or a single property, a model may not be necessary, as the overhead might not justify the use. However, when dealing with dynamic or reusable data, especially in SwiftUI apps, a model is highly recommended. By conforming the task model to the identifiable protocol, each task is assigned a unique identifier, enabling seamless integration with SwiftUI's dynamic views like for each. This ensures efficient rendering and updating of tasks in a list or grid while keeping the code clean, organized, and scalable for future enhancements. To resolve the naming conflict between task models, we need to refactor the model name in the calendar view to prevent collision with the task model in the home view. Let's modify the calendar view implementation. First, open the calendar view file and use the find and replace function, Command plus F. The find and replace navigator in Xcode can also be accessed through the Project Navigator interface. Press Command plus 4 to quickly open the Find Navigator. This powerful tool allows you to search and replace text across your entire project, specific files, or selected areas. The interface provides options to refine your search with case sensitivity, regular expressions, and whole word matching. In the Replace dialog, enter Task with a capital T in the Find field and Calendar Task in the Replace field. Make sure to enable case sensitivity to maintain proper Swift naming conventions. You'll see approximately 10 occurrences of task. Carefully replace each instance individually to ensure you don't accidentally modify unrelated code. After replacing all instances, the compiler error regarding invalid pre-declaration will be resolved, and your SwiftUI preview should resume functioning. Next, we define a TaskViewModel class that manages a collection of tasks in a SwiftUI application, utilizing the power of published property wrapper, a key feature that acts as an automatic notification system to announce data changes throughout your application. This class conforms to Observable Object Protocol, creating a reactive system where SwiftUI views automatically update when data changes. When you mark properties with published as done with our tasks and filtered tasks arrays, SwiftUI establishes an automatic observation system that refreshes any views depending on these values, eliminating the need for manual view updates. Each task in the array is structured with specific information: a title, describing the task, a subtitle, providing additional context, and an associated image name for visual representation. The class implements a key filtering function that updates the filtered tasks based on a search query using Swift string manipulation capabilities. If the search query is empty, it displays all tasks. Otherwise, it filters tasks where either the title or subtitle contains the search text, case insensitive. This filtering functionality, combined with the reactive published properties, creates a seamless search experience where users can quickly find specific tasks and see results update in real time. The TaskView model serves as a central data manager, handling both the storage and manipulation of task data while maintaining a clean separation between the data logic and the user interface, demonstrating how published properties facilitate efficient state management and view updates in SwiftUI applications. Now, we can start implementing the search feature using our custom search bar in Home View. Let's understand the 3 essential property wrappers that power our search functionality. First, state object private var view model equals task view model. The task view model serves as our single source of truth, managing all task-related operations. It maintains the list of tasks and filters them based on a search query, exposing a filtered tasks property that the UI can bind to and update dynamically. StateObject is used to create and own an instance of an observable object, ensuring that the instance's lifecycle is tied to the view. This property wrapper ensures that viewModel persists during view re-renders and doesn't recreate unnecessarily. Second, StatePrivateVR search text equals empty strings. For handling user input, we leverage state with our search text property. This creates a reactive binding between our search bar component and the actual search query. As users type, SwiftUI automatically updates the view to reflect these changes. Finally, StatePrivateVR is search bar visible equals false. The search bar's visibility is controlled by is search bar visible. This state property enables smooth transitions between showing and hiding our search interface, creating a cleaner user experience. These properties work together to create a seamless search experience. When users type in the search bar, search text updates instantly. The viewModel filters tasks based on the current search text value. Our UI automatically refreshes to display the filtered results. The search bar smoothly appears and disappears based on is search bar visible. Remember, StateObject is perfect for view models that need to persist, while state works best for simpler, view local properties, like our search text and visibility toggle. Next, we'll add a binding property to the user greeting view to controls the search bar's visibility. Add binding var is search bar visible, bool to the view's properties. Next, create a search toggle button by implementing a button with the magnifying glass icon. The button uses with animation to smoothly transition the search bar's appearance. For the search functionality itself, add binding var, search text, string to the search bar view to enable two-way data binding with the parent view. This binding will automatically update the search results as the user types. Let's implement the search functionality in our home view by restructuring its layout and integrating our search components. First, let's break down the implementation steps. Start by clearing your existing VStack and its contents to create a clean foundation for our new search interface. Create a new VStack with 16 points of spacing to ensure proper visual hierarchy. The user greeting component is a custom view that displays a welcome message and manages the search bar's visibility. To enable two-way communication between views, pass the binding with is search bar visible, $ is search bar visible. This binding allows the user greeting component to control the search bar's state. For the search functionality implementation, we'll use SwiftUI's conditional rendering with these components. The search bar view handles user input through a binding with search text. As users type, this binding automatically triggers view updates. Below the search bar, implement a scroll view to create a smooth scrolling container for search results. Within this scroll view, add a VStack with leading alignment and 16-point spacing to display filtered tasks using our task item views. To style the current task's header text, apply the following modifiers. Use .headline to set the appropriate text size, enhance visual emphasis with font weight .semibold, and maintain your app's visual consistency by applying .foreground color .app text primary for the text color. Implement the task list using for-each to iterate through filtered tasks. Remember that your task model must conform to the identifiable protocol. Each task item view will display task properties from your data model. For real-time search functionality, the view model's filtered tasks property updates automatically based on search text input. Add 8 points of padding above your results container to maintain proper spacing between the search bar and results. Now let's implement the main dashboard view of our SwiftUI app. The dashboard will be visible when the search functionality is inactive, controlled by the @state property is search bar visible. We'll use a simple conditional statement if exclamation point is search bar visible to manage the view's visibility. When users activate the search feature, the dashboard will seamlessly transition to the search results interface. The dashboard structure consists of a scroll view with a vertical scroll direction containing 3 key components arranged in a VStack. At the top, we'll place the task status card to display your task progress metrics. Below that, you'll find the task category tabs for easy navigation between different task categories. Finally, we'll implement the Tasks List section using custom task item views, which will present each task's information in a consistent and visually appealing format. To maintain proper view hierarchy, make sure to embed the existing VStack content within the if exclamation point is search bar visible condition block. To implement a functional search feature, you'll need to add two essential SwiftUI modifiers. First, add .onChange of search text to monitor real-time changes in your search field. This modifier executes a closure whenever the user types, using the pattern _new value in. Here, we ignore the previous value, represented by _ and capture the current search text, new value, which will pass to our view model's filter tasks with method. Second, implement .onAppear to initialize your view state properly. This modifier calls filter tasks with empty strings when the view loads, ensuring all tasks are visible before any search is performed. By combining these modifiers, you'll create a responsive search experience that maintains a clean initial state. Remember to add both modifiers to the main Z stack to enable the complete search functionality. To enhance your search bar's visual appeal and create a more fluid user experience, let's implement a transition animation. This animation combines two key elements, an opacity fade and a smooth sliding motion from the top edge. When your search bar appears or disappears, these effects work together simultaneously. The view gracefully fades in/out while sliding from the top edge, creating a dynamic and polished transition that significantly improves your app's interface. This movement is controlled by a spring animation, which adds a natural, bouncy feel to the motion. The spring animation is configured with specific parameters. The response time of 0.5 seconds determines the animation's initial reaction speed, acting like a spring stiffness. Lower values around 0.3 seconds would create a snappier but potentially jarring motion, while higher values near 0.8 seconds would result in a smoother but possibly too gradual transition. The damping fraction of 0.7 creates an optimal bounce effect that prevents the animation from feeling either too rigid or too loose. Values closer to 0 would introduce more pronounced oscillations, while values closer to 1 would eliminate the bounce entirely, resulting in rigid movement. Finally, the blend duration of 0.5 seconds ensures smooth integration with other UI transitions, preventing visual disruptions when the search bar interacts with other elements and harmonizing the opacity fade with the sliding motion. This combination creates a smooth, engaging transition that enhances the user experience by making the search bar's appearance and disappearance feel dynamic and polished. Thank you for watching. If you found this tutorial helpful, please support our channel by subscribing and giving this video a thumbs up. Stay tuned for our next tutorial where we'll explore more advanced SwiftUI techniques. See you in the next video.